All right, welcome. Here I'm going to continue with part 4 of the statistical review. The topics that I'm going to cover here are the discrete uniform distribution and the binomial distribution. Both of these are forms of discrete probability distributions, or they're two specific discrete probability distributions. The discrete uniform probability distribution is the simplest in some sense, and it has a formula that is shown there, 1 over n, where n is the number of values that the random variable could take on. So that's the probability function that you have for the discrete uniform probability distribution. So in this case, all values that the random variable can take on are equally likely. So all possible outcomes have the same probability. They're all equally likely. So an example would be you have employees, and they can be given an annual performance rating of 1, 2, 3, 4, or 5. Suppose that all ratings are equally likely. So 1 is just as likely as 5, 2 is just as likely as 5, 3 and 2 are just as likely, and so on. So since there are 5 ratings or values that the random variable can take on, the probabilities are going to be 1 over 5 for each of the possible values. So in the table there, the f of x, the probability is 0.2, 1 over 5, for each of the possible outcomes. Now in this case, you can compute the average rating, or mean. It's going to be 3. If that's not clear, I recommend you pause the video, or at the end of the video, you double check that using the formula. So you would have 1 times 0.2 plus 2 times 0.2 plus 3 times 0.2 and so on. To get that average of 3. You can also find the probability of an employee receiving a rating of 5 or any other value. In this example, it's 0.2. So it's just reading off of the table that was shown before. It's just going to be 1 over n, whatever n happens to be in a given example. Another discrete distribution is the binomial distribution. So a binomial experiment has the following characteristics. The experiment is going to have n identical trials. There are going to be 2 outcomes that are possible, so each trial can end in either success or failure. And then the probability of success is known ahead of time. We're stating this, we've gotten this either from some previous study, something that we've done. We happen to know what p, the probability of success, is. Since there are just 2 outcomes, success or failure, the probability of failure is 1 minus p. And those values are the same for all trials. So all trials are, in a sense, the same then. They have the same probabilities. And the trials are independent. Now, suppose you're interested in the number of successes that occur in the n trials. So let's suppose you have 20 trials and you want to know the probability of getting 5 successes. Right? So in this case, the number of trials, n, would be 20. The number of successes that you're looking for is 5, or at least you're looking for a probability associated with x being 5. X would be the number of successes again. So the formula for this is given here on this sheet, and you'll notice perhaps that it has a few different features. It maybe looks a little complicated, but many calculators have an option to be able to plug this in perhaps a little more quickly. So here we've got, again, x is the number of successes, p is the probability of success, but you see that coming in here, the p, but you also see 1 minus p, probability of failure over here. N is the number of trials, and that enters in a couple of places. It enters in here. Also, you'll see n here and in this exponent over here. So then you have the answer to this, right? The f of x is the probability of getting x successes in n trials. And again, we have this n factorial. Right? So n factorial is just to remind us, right, what factorial is here, right? So we also have x factorial and n minus x factorial, but this Just a reminder what this symbolism is for this exclamation mark. It means factorial. So that's the formula that you have for the binomial probability distribution. It can be broken down into two basic parts, just conceptually to think about here. So in this part over here on the left-hand side, it's the number of experimental outcomes providing exactly X successes in N trials. So think about this as maybe the counting rules that we're reading over here on the left-hand side. And on the right-hand side, we've got the probabilities going on in here, and it's the probability of a particular sequence of trial outcomes that have X successes and N trials. All right, and then this would be on the left again, the number of different possible sequences that there would be. So just a little bit better, perhaps, understanding of the formula. All right, consider the following example. We have promotional codes. A store manager wants to find the probability that a group of customers will use a promotional code for their purchases. From past experience, the store manager estimates the probability that any one customer uses a promotional code is 0.3. The question is, what is the probability that 2 of the next 3 customers will have a promotional code or use? We can identify that this 0.3 here is our value P. 2 of the next 3, we've got 3 customers coming in. This is our N, that's the experiment. Each customer constitutes an experiment. 2, this value here, this is our value X. What the manager is interested in is finding the probability that 2 of those 3 will make a purchase. So those are the key values in there. Does this fit the other characteristics? Probably. It's likely that each customer acts independently from every other customer. There are a set number of trials here, 3, and we have a probability of success, and that's presumably the same for each customer. At least that's the assumption going on here. So it looks like it will fit our requirements for binomial distribution. Now, then, to punch this in and get an answer out here, we've just got the formula again, and you see there the N is 3, the X is 2, and the probability is 0.3. So all of these values in here, the 2, the 3, again 3 and 2, all of these values come from the problem, right? So the 0.3 here, right, that was our P. We're just plugging them in. If we crank through this, and you can pause this to check your answer or write it down and check later, but you should get out 0.189. Right, so that's one example. And then in another example, and I'll encourage you to pause the video here to work through this one, but is you have a sales agent that makes 10 contacts during the day. Each contact ends in a sale or no sale, and the probability of making a sale is 0.25. What is the probability of making exactly 4 sales? So I encourage you to pause this to work through and get the answer, and then check here with you in just a second. So hopefully you got an answer of 0.145998 as the probability of making exactly 4 sales. If you didn't get that, you can go back and double check your values, make sure that you're using the right formula to get that through. All right. The binomial distribution also has an expected value and a variance and standard deviation. You can go back to a different video to check again the basic setup for what we mean with expected value and variance. But here the formula for the expected value is N times P, the number of trials times the probability of success. That will give us the expected value. When we're looking at getting the variance, what gets changed here or added on is you've got this expected value here, n times p, and then simply multiply it by the probability of failure, 1 minus p. And the standard deviation, of course, is just taking the square root of that, as you see here. So there are the basic formulas for getting the expected value and the standard deviation when we're looking at the binomial distribution. An example with that, going back to the promotional codes example, we had the next 3 customers and they had a probability of using a promotional code of 0.3. So we'd have 3 times 0.3 gives us 0.9. Then if we want to find the variance, we're going to take that same 3 times 0.3, the expected value, 0.9, multiply it by, in this case, 1 minus 0.3, or 0.7, and we find that we get 0.63. You can slow this down or pause this and check using your calculator. And then to get the standard deviation, simply take the square root and you find 0.79. So then let's think about another example or give you an opportunity to work through this on your own. So I encourage you to pause the video and try this. But going back to the example with the sales agent making 10 contacts during the day, and again, the contact ends in sale or no sale, and the probability of making a sale is 0.25. So what are the expected sales and the standard deviation for the number of sales? So go ahead and pause the video and take a minute to make those 2 calculations before going forward. All right, hopefully what you found was an expected value of 2.5, just taking the 10 times the 0.25, and then for the standard deviation you would have taken the 2.5 and multiplied it by 0.75. That would be the 1 minus 0.25, and then taking the square root of that, and hopefully you got an answer of 1.369.